The Committee on Science, Space, and Technology will come to order. Welcome to today's hearing titled Astrobiology, the Search for Biosignatures in Our Solar System and Beyond. I'll recognize myself for 5 minutes for an opening statement and then recognize the ranking member. The search for exoplanets and Earth-like planets is a relatively new but inspiring area of space exploration. Scientists are discovering solar systems in our own galaxy that we never knew existed. As we learn more about these new worlds, reasonable questions to ask are, what could we find on these planets? Do the atmospheres of these planets provide biosignatures that would indicate the presence of some form of rudimentary life? And what would be the implications of such a discovery? The discovery of even microbes on another planet would be the most newsworthy story in decades. It could affect the way we view our place in the universe, and it could create increased interest in the core disciplines of astrobiology, including chemistry, physics, geology, and biology. The United States has pioneered the field of astrobiology and continues to lead the world in this type of research. The publication of scientific findings illustrates the field's growth and growing popularity in the past 20 years. A sample of professional papers published in Science magazine between 1995 and 2013 shows significant growth in the field of astrobiology. For example, in 1995, fewer than 50 papers were published on astrobiology. By 2012, that number had increased to more than 500. In 1995, fewer than 500 scientific reports cited astrobiology, but by 2012, it was almost 12,000. Astrobiologists study the atmospheres of planets to determine whether or not some of these newly discovered planets possess possible signs of life, such as microbes or some form of vegetation. Scientists believe that such planets would produce certain gases in their atmospheres. For example, when examined from a distance, Earth's atmosphere contains large amounts of oxygen. When looked at through a large infrared telescope, the biosignature would be detectable from a distant point in space. Using the infrared camera on the Hubble Space Telescope, two teams of scientists from the University of Maryland, NASA's Goddard Space Flight Center, and the Space Science Telescope Institute announced just yesterday that they had found signatures of water in the atmospheres of 5 exoplanets. The planets are similar to what are called hot Jupiters, too large and gaseous to contain any form of known life. However, the techniques used in this case are also being used to examine the atmospheres of other planets. Future telescopes, including the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the Wide Field Infrared Survey Telescope, will help us discover more about the atmospheres of exoplanets and whether or not microbes or other forms of life could exist there. I look forward to hearing how research in astrobiology continues to expand this fascinating frontier. And that concludes my opening statement, and the gentlewoman from Texas, Ms. Johnson, is recognized for hers.
Thank you very much, Mr. Chairman, and good morning, and welcome to our distinguished panel of witnesses. There is no denying humankind's interest in establishing whether life exists elsewhere in the universe. People have probably speculated on that possibility since immemorial. The question of whether there is life beyond Earth got increased attention this year following the Kepler Space Telescope's discovery of Earth-sized exoplanets in habitable zones around other stars, and Curiosity's finding of traces of water in the Martian soil. Astrobiology, as we will hear during this hearing, is an interdisciplinary field that makes use of many fields of science to investigate the possibility of life on other worlds. As might have been guessed, NASA has played a major role in astrobiology's development as a former discipline. NASA's Viking missions to Mars, launched in 1976, included 3 biology experiments designed to look for possible signs of life. The scientific excitement generated by the Viking mission new results from solar system exploration and astronomical research programs in the mid-90s. And advances in the fundamental biological sciences led to the establishment of the NASA Astrobiology program in 1996. Today, NASA's astrobiology program consists of 4 elements: grant programs, technological activities aimed at the development of new scientific instrumentality, technological activities aimed at the field testing of new scientific instruments, and the NASA Astrobiology Institute. In addition, astrobiology has become a cross-cutting theme of all of NASA's space science endeavors. For example, rather than being standalone investigations, many planetary science and astronomy missions work together in their search for life in the universe. Mr. Chairman, I would be remiss were I not to make note in continuing to provide adequate funding to NASA science programs is of critical importance if we are to continue to make progress in astrobiology as well as other important scientific fields. I hope that Congress recognizes the vital contributions of ongoing and future NASA space science missions in answering whether there is life in the universe. This hearing is an opportunity to shine light on these contributions, and I look forward to hearing from our witnesses. I thank you and yield back.
Thank you, Ms. Johnson. I'll now introduce our witnesses. Our first witness is Dr. Mary A. Voytek. Dr. Voytek became Senior Scientist for Astrobiology in the Science Mission Directorate of NASA Headquarters in 2008. Dr. Voytek came to NASA from the U.S. Geological Survey, where she headed the Microbiology and Molecular Ecology Laboratory. Dr. Voytek has served on advisory groups to the Department of the Interior, Department of Energy, the National Science Foundation, and NASA, including NASA's Planetary Protection Subcommittee. She received a bachelor's in biology from Johns Hopkins University, a master's in biological oceanography from the University of Rhode Island, and a PhD in biology and ocean sciences from the University of California. Our second witness is Dr. Sara Seager. Dr. Seager is an astrophysicist and planetary scientist at the Massachusetts Institute of Technology. Professor Seager chairs a current NASA Science and Technology Definition Team study of the star shade concept for space-based direct imaging to find and characterize other Earths. Before joining MIT in 2007, Professor Seager spent 4 years on the senior research staff at the Carnegie Institute of Washington, preceded by 3 years at the Institute for Advanced Study in Princeton, New Jersey. She is a 2013 MacArthur Fellow, winner of the Genius Grant, also the 2012 recipient of the Raymond and Beverly Sacker Prize in the Physical Sciences, and the 2007 recipient of the American Astronomical Society's Helen B. Warner Prize. She received her Bachelor's of Science in the Math and Physics Specialist Program from the University of Toronto. She also holds a PhD in astronomy from Harvard University. Our third witness is Dr. Stephen Dick. Dr. Dick currently holds the Baruch S. Blumberg NASA Library of Congress Chair in Astrobiology at the Library of Congress. He served as the Charles A. Lindbergh Chair in Aerospace History at the National Air and Space Museum from 2011 to 2012, and as the NASA Chief Historian and Director of the NASA History Office from 2003 to 2009. Prior to that, he worked as an astronomer and historian of science at the U.S. Naval Observatory in Washington, D.C. for 24 years. He obtained his B.S. in astrophysics and M.A. and Ph.D. in history and philosophy of science from Indiana University. We welcome you all and look forward to your testimony, and Dr. Voytek will begin with you.
Thank you. Mr. Chairman and members of the committee, thank you for the opportunity to appear today to discuss the topic of astrobiology. For thousands of years, humans have looked up at the stars and wonder whether life exists beyond our home planet. This curiosity was renewed with the latest discoveries by NASA's Kepler mission, totaling 3,500 new candidate planets outside our solar system. With Kepler's help, more than 800 potential worlds have now been confirmed orbiting stars other than our sun. And at least 5 of these are Earth-sized and orbiting within the habitable zone of each of their stars. This reminds us just how important NASA's work is to the understanding of the universe and the potential for life beyond our solar system. A companion question that even every child wonders is, where did I come from? Astrobiology seeks to answer these enduring questions. What is astrobiology? Astrobiology is the study of the origin, evolution, distribution, and future of life in the universe. It addresses three basic questions that have been asked in various ways for generations. How does life begin and evolve? How does life exist elsewhere in our universe? And what is the future of life here on Earth and beyond? In striving to answer these questions, experts in astronomy, astrophysics, earth and planetary sciences, biology, chemistry, and many other relevant disciplines participate in astrobiology research to achieve a comprehensive understanding of biological, planetary, and cosmic phenomena and the relationships among them. This multidisciplinary field encompasses the search for habitable environments in our solar system, as well as habitable planets outside of our solar system. Astrobiology embraces laboratory and field research into the origins and early evolution of life on Earth, the search for evidence of habitability and life on Mars and other bodies in our solar system, as well as studies of the potential for life to adapt to future challenges both here on Earth and beyond. It is a cross-cutting theme in all of NASA's space science endeavors. It knits together research in astrophysics, earth science, heliophysics, as well as planetary sciences. The NASA astrobiology program is guided by a community-constructed roadmap that's generated every 5 years. The ongoing development of this roadmap embodies the composition of diverse scientists, technologists from government, universities, and private institutions. These roadmaps outline multiple pathways for research and exploration and contribute to our decisions on how our investments might be prioritized and coordinated. NASA established its current astrobiology program in 1996. However, NASA studies in the field of exobiology, a predecessor to astrobiology, date back to the beginning of the U.S. space program. We are proud of the results of our 50 years of cutting-edge research. In the 20th century, astrobiology has focused on a growing number of NASA missions. As mentioned earlier, with Kepler's mission, we have been able to detect Earth-sized planets within the habitable zones around distant stars. These potentially habitable planets will expand our search for life beyond our own solar system. Mars also continues to be an area of interest, with the Curiosity rover mission currently assessing the potential habitability of that planet. In fact, results from that mission have already shown that in the past, Gale Crater could have supported microbial life. However, since Earth is the only known example of an inhabited planet, the search for life in the cosmos begins with our understanding of life on Earth. So studying the origins and evolutions of life on Earth improves our ability to recognize and characterize life in its many imagined and yet potentially possible forms. In 2010, astrobiologists found that a number of microbes from Earth could survive and grow in the low pressure, freezing temperatures and oxygen-starved conditions seen on Mars. Overall, astrobiologists have discovered life in numerous extreme environments on Earth, such as volcanic lakes, in glaciers, sulfur springs. We have also found life in extraordinary forms, ranging from bacteria that consume chemicals toxic to most life, to microbes that live under high levels of gamma or ultraviolet radiation. These discoveries have taught us that life is tough, tenacious, and metabolically diverse, and highly capable to adapt to local environmental conditions. Knowledge gained through the astrobiology research reveals new possibilities, what else might be out there, and how we might be able to find and recognize it. An example of astrobiology technologies that have proved useful for broader application is the chemistry and mineralogy instrument that was developed for the NASA Curiosity rover. CheMin is a highly sensitive instrument that can identify and quantify the minerals present in the Martian rocks and is currently being used in a commercial spin-off for a variety of purposes, including hazardous material identification, mineral prospecting, artifact preservation in museums, and even detection of counterfeit pharmaceuticals in developing countries. In conclusion, life is a central theme that unifies NASA's science program. The science of astrobiology aims to achieve a better understanding of our own world and the life that it hosts. After 50 years, we are now in an era that can finally provide data on whether or not we are alone in the universe. This is an agenda for inspiring the next generation of explorers and stewards to sustain NASA's mission of exploration and discovery. Again, thank you for the opportunity to testify today.
Thank you, Dr. Voytek and Dr. Seager.
Mr. Chairman and members of the committee, we're truly at a unique time in human history. We stand on a great threshold in space exploration. On the one side, we now finally know that small planets exist and are common. But on the other side lies the possibility to find the true Earths with signs of life. The point I want to make is this is the first time in human history we have the technological reach to cross the great threshold. And as already explained, to infer the presence of life on an exoplanet, we will search for biosignature gases, which we define as a gas produced by life that can accumulate in an atmosphere to levels that we can detect remotely by large telescopes. The example on Earth is oxygen, which fills our atmosphere to 20% by volume. But without plants and photosynthetic bacteria, we would have virtually no oxygen. So our search for biosignature gases is a search for gases that we call it don't belong, that are produced in huge quantities that can be attributed to life. And I'd like to just say briefly that NASA-supported astrobiology has been absolutely foundational in biosignature gas research by connecting microbiologists with astronomers and geologists and planetary scientists. The main point I want to make, a main point, is that we will not know if any exoplanet biosignature gas is produced by intelligent life or if it's produced by simple single-celled bacteria. Right now, we don't have any planets we can study for biosignature gases. The Kepler planets, while small, are too far away and too faint for any atmosphere follow-up studies. NASA's TESS mission, led by MIT and scheduled for launch in 2017, is a two-year all-sky survey of more than 500,000 bright stars. Now, while TESS will not reach down to the true Earths, it will find dozens of rocky planets transiting small cool stars. The reason we're so excited about TESS is that dozens of the TESS rocky planet atmospheres can be studied by the James Webb Space Telescope, and a few of these planets are likely going to be in the star's habitable zone. So while the chance for life detection with the James Webb is very, very, very small, if life really is everywhere, we actually have a shot at it. Now, to up our chances of finding life on an exoplanet, we need to move to a different kind of planet finding and characterizing technique, because the TESS James Webb combination focuses on a rare type of planet, a transiting planet that has to be aligned just so it goes in front of the star as seen from Earth. That's actually the easiest way to find small planets right now, but it's not the best way because we need to be able to search all of the nearby sun-like stars. So direct imaging is the starlight blocking technique, and it's extremely challenging because our Earth at visible wavelengths is 10 billion times fainter than our sun. 10 billion is such a huge number. This is a massive technological challenge. But NASA is studying two different direct imaging techniques. One is the so-called internal coronagraph, where specialized optics are placed inside the telescope. But the telescope has to be incredibly specialized to be exceptionally thermally and mechanically stable. The other technique is the star shade, that is putting a giant specialized screen, tens of meters in diameter, and find information tens of thousands of kilometers from a telescope. The star shade blocks out the starlight, so only the planet light reaches the telescope. Now, the internal coronagraph is more mature, but the star shade is likely our best way to find Earths in the near future because the star shade does all the hard work, and we can have a simple telescope, relatively simple telescope with a very high throughput. I wanted to just briefly give you my vision for how to proceed after the James Webb Space Telescope and the TESS mission, is that we need a small space telescope mission to prove the direct imaging technique and to deliver exoplanet science. We need to demonstrate both the internal coronagraph and the star shade because we don't know which one will succeed on a larger scale, and both actually may be needed. The internal coronagraph technique right now is under study for instrumentation on AFTA. You called it on AFTA. We'll be able to observe some giant planet atmospheres. The star shade and telescope system could be supported under a so-called probe class category and could reach down to a couple of dozen Earths. Now, here's the thing. If we want to really be able to find planets with biosignature gases, we need hundreds of Earth-like planets. We need to search thousands of sun-like stars. So for the intermediate future, we will require a large visible wavelength telescope with a large mirror exceeding 10 meters in diameter. So that is a big thing for the future, but that's what it will really take if we want to up our chances of success. So I just wanted to briefly say that the level of public interest in exoplanets has accelerated literally almost exponentially in the nearly 20 years I've been in this field. the number of people who approach me on a continual basis, from high school students to MIT students to other university students to literally people all around the world, to CEOs of small tech companies, to retirees. These people aren't just interested in exoplanets, they want to work on exoplanets. And so I'll just close by leaving you with the vision that this search for finding life beyond Earth is so revolutionary. It will really change the way that we see our place in the cosmos, such that we believe hundreds or 1,000 years from now, people will look back at us collectively as those people who first found the Earth-like worlds. And so it could be our greatest legacy. We just need to, it's within our power, based on our near-term decisions and investments, to actually make this happen. So, Mr. Chairman and Committee, this concludes my remarks.
Thank you, Dr. Seager and Dr. Dick.
Chairman Smith and Ranking Member Johnson and members of the committee, thank you for the opportunity to testify today on the subject of the past and future of astrobiology. I do so not as a practitioner in the field, but as an historian of science who for 4 decades has documented the debate over life beyond Earth. In that role, I can say that this is a subject rich in history and promise, and one that fascinates the American public. During my time as NASA chief historian, everywhere I went, people wanted to know about life on other worlds, and they still do. Astrobiology raises fundamental questions and evokes a sense of awe and wonder as we realize perhaps there is something new under the sun and under the suns of other worlds. The key discoveries in astrobiology over the last decade have evoked that sense of awe and wonder. High on the list must be the discovery of planets beyond our solar system. Those so-called exoplanets are the very first goal of the NASA astrobiology roadmap. Ground-based telescopes, as well as the Hubble and Spitzer telescopes, have all contributed to these discoveries, and NASA's Kepler spacecraft has opened the floodgates. By the end of 2013, almost 1,000 planets have been confirmed. Thousands more are awaiting confirmation. Smaller and smaller planets are being detected, including super-Earths and Earth-sized planets. A second highlight is the continued search for life in our solar system, Goal 2 of the roadmap. A fleet of spacecraft over the last decade has demonstrated that Mars had enough liquid water in the past to be habitable for life. Spacecraft have probed the icy moons of the outer solar system, including the Jovian moon Europa and the Saturnian moon Enceladus. The still ongoing Cassini-Huygens mission has found on the Saturnian moon Titan an atmosphere believed to be rich in prebiotic organic compounds and lakes of methane on the surface of that satellite. And just a few months ago, Cassini captured an image of Earth, a pale blue dot against the darkness of space. Another of the highlights of the last decade has been to demonstrate further the tenacity of life in extreme environments. Goal 5 of the astrobiology roadmap. Life has been found in hydrothermal vents deep below the ocean, kilometers below the ground, way above the boiling point of water, way below its freezing point. The point is that life is more tenacious than once thought, and so may arise on planets under conditions once thought unfavorable. Genomic analysis of these microorganisms continues to shed light on how they function. Among the critical issues in the search for life in our solar system during the next decade will be continued research program on past and present life on Mars, employing spacecraft such as MAVEN, which was just launched 2 weeks ago, as well as continued field and laboratory research on the origins, limits, and future of life on Earth and other planets. Beyond the solar system, the challenge now is to classify and characterize the newly discovered planets, as well as to search for even smaller ones. Over the next decade, spacecraft such as TESS will search for rocky planets and stars, and the James Webb Space Telescope will further characterize those planets and their potential for life by searching for biosignatures in their atmospheres. This is Goal 7 of the roadmap. I'd like to say also, in my view, renewing the search for radio and other artificial biosignatures as part of the search for extraterrestrial intelligence, SETI, would enhance NASA's astrobiology program and repair the artificial programmatic divorce that now exists between the search for microbial and intelligent life. No biosignature would be more important than a radio signal from another civilization on one of those newly discovered planets, perhaps, especially if they have something to say. In concluding, I'd be remiss if I failed to mention that among the issues and challenges for the next decade are those related to astrobiology and society. Indeed, the astrobiology roadmap recognizes as one of its 4 implementation principles a broad societal interest in its endeavors. Astrobiology raises profound questions with respect to the impact on society, what will be the effect on our worldviews, our philosophies and religions, if we discover microbial or intelligent life beyond the Earth. Are there useful analogies that will help us to evaluate societal impact. History indicates that the recognition, the discovery, or the failure to discover extraterrestrial life is likely to be an extended affair, as in the debates over the Viking spacecraft results and the ALH 84001 Mars rock controversy. These are the kinds of societal aspects of astrobiology that I'm now studying as part of my time at the Library of Congress. Others are also studying these societal impact questions, especially in the last 5 years, since the NASA Astrobiology Institute has supported a roadmap and a focus group on astrobiology and society. Finally, let me say that, in my view, astrobiology embodies the most important ideals of discovery, exploration, and inspiring our explorers for the next generation. No better hook exists, in my experience, to get students interested in science than the tantalizing and interdisciplinary questions of astrobiology. I always like to quote Nobelist Baruch Blumberg, the first director of the NASA Astrobiology Institute, and the inspiration behind the Blumberg NASA Library of Congress chair that I hold now at the library's Kluge Center, which brings together scholars and policymakers. Astrobiology, Dr. Blumberg said, is in the best tradition of our species and in the best American tradition dating back to Lewis and Clark, to ask great questions, to explore our world and other worlds, to infuse our culture with new ideas, and to evoke that sense of awe and wonder as we discover the true place of our pale blue dot in the universe. Thank you.
Thank you, Dr. Dick. Let me address my first question to Dr. Voytek and Dr. Dick. First of all, this is an exciting subject, even an inspirational one. And it's also, I think, worth noting that space exploration, including the kinds of exploration we're talking about today, attracts bipartisan interest and bipartisan support. So that's nice from the point of view of members of Congress. And also the subject has literally caught the public's imagination, and that is something to build on and something to encourage as well. But Dr. Voytek and Dr. Dick, you both mentioned the astrobiology roadmap. The last official roadmap was 2008. Supposedly there's one every 5 years. I understand that 2013 is actually coming out in 2014, May, June, thereabouts. But my question is this: when it comes to astrobiology, what should be our goals today? If you could write the roadmap, obviously it's changed a lot in the last 5 years, but what should be our astrobiology goals today? Dr. Voytek?
So the current roadmap is being developed to align,
what would be your goals?
What my goals would be to better enable the search for life outside of Earth, which includes really pushing our knowledge base about what is possible for life in general. So to extend our research on extreme environments and push it to the limit in terms of what kinds of conditions to better establish habitability off the Earth.
Right.
And I believe that we also need to push hard in the area of synthetic biology to understand the basic building blocks of life to enable a better search strategy for the potential types of life. I anticipate that the first life we find is likely to be microbial, very relatively simple life form, and that it will be essential to know, as life did on this planet, it made itself from what was around it. It's likely it will do the same on other planets, and so we need to be mindful of what other possibilities there are.
Okay, thank you. Dr. Voytek, Dr. Dick.
Well, aside from what's already been said, I'd like to see a voyage to Europa to find out what's under the thick ice, what's swimming around down there, perhaps, or also out to Saturn with Enceladus and to detect more of what those water spouts that are shooting out of Enceladus, what the biosignatures might be from there.
I think Europa is already on the list, but we'll have to expedite that.
Right.
I agree. Okay.
Also, I would say, as I mentioned, that I think it would be great to repair this divorce between the search for microbial and intelligent life by including more a robust program on SETI.
Okay, good. Thank you, Dr. Dick. Dr. Seager, I liked your word revolutionary when it comes to the possible discovery of microbes or other interesting forms of life elsewhere and on other planets. What I wanted to ask you, and you went into some detail as to how we might be able to detect these biosignatures, but could you give us a hopeful timeline? When might this occur? And I know that we've gotten certain dates for the launches of these various telescopes, but some people think we might actually achieve some breakthroughs with the devices and the equipment we have today. But I just want you to speculate. Do you think in what time frame might we expect to find some evidence of, say, microbial life elsewhere in the universe?
I always like to start by saying scientists never like to speculate. We always like the facts. But we always do, correct. So let's say our input is that just for argument's sake, if every star has an Earth and every Earth has life, then we have a great chance of finding the first signs of it with the TESS James Webb Space Telescope combination. It's likely that it's not that common. We see evidence already that not every star has an Earth-sized planet in the habitable zone, but many do. And in that case, we need to go to a direct imaging mission in space. And there's no plan on the books for that. We have lots of studies going on. If that one could be implemented, when it is launched, it would take a few years. And in that case, we also have to be lucky. If it's correct that 1 in 5 stars like the Sun now has an Earth and every one of those has life, then we would be able to find signs of life with that relatively small space telescope mission. Okay? My best guess, if you wanted the honest, very conservative answer, if I have to come back and be the one who has to hold the responsibility for this, I would say we need that next generation telescope beyond the James Webb, the big telescope in space. So we need to invest in technology now so this can actually happen at some point. And once that one goes up, it would just be a matter of a few years to survey enough stars for planets and find them. So I've given you the most optimistic case, somewhat unrealistic, that the James Webb finds it. The least optimistic case, we need to find out how to put a large mirror in space to search enough to have enough chance.
Okay. Most optimistic then, next 5 to 10 years?
Yes, the most optimistic is within a decade.
Okay.
But I don't want to leave you with just being optimistic because we really do need to invest in the future.
Right. Understand that. Thank you, Dr. Seager. Last question is for you all. Starting with Dr. Voytek. What can we do to expedite the process? And that's a pretty general question. Some of the answers have already been given, the development of these various telescopes, tests, and so forth. But what can we as members of Congress do to expedite the process? I have a hunch part of the answer is going to be funding, but so be it.
Well, I was going to say continued support. You've already provided, Congress and the administration has provided excellent support to the Planetary Sciences Division and Astrophysics and Science Mission Directorate in general. And so we need your continued support. I know that funding is tough, but that's the best thing you can do. And yep.
Okay, if we make it a priority, we can achieve that 5 to 10 year time frame, perhaps. Dr. Seager.
I would say that keeping our outreach abilities in the university system with the experts who are actually working on the field is so important. I think people don't quite understand how often, you think outreach happens maybe at the museum or elsewhere, but as individuals, we actually do a huge amount of this. And it's sort of inspiring the next generation, so we make sure we have that pool of people to keep us not only at the forefront of space technology, but in biology and keeping this interest moving along. I think that's the best investment we have.
Great. Okay, Dr. Dick.
Aside from funding, I think just the idea that we know that Congress is behind the program, including, for example, the SETI program. I think that is still seeing the repercussions from 20 years ago when that program was canceled. And NASA is not forbidden from funding that, but they realize that Congress has sort of discouraged that 20 years ago.
Right. I think there's more interest today and more possibilities today with the discovery of all these exoplanets.
Exactly.
So that might trigger that as well.
Right.
Thank you, Dr. Dick. My time is way over. The gentleman from Texas, the ranking member, is recognized for her questions.
Thank you very much. I guess this question is to all of you. To what extent are the interagency and international collaboration important to the astrobiology, and what, if anything, is needed to facilitate that collaboration to maximize the progress and findings?
I will start with that. The astrobiology program, when we established the Institute, part of its charter was to explore means to enhance collaboration amongst all nations that are interested in the questions that are addressed by astrobiology. And we've been very successful in making affiliations and collaborations, and each government has brought their own resources to bear, and we just try to facilitate work together because just as it is multidisciplinary, it is also a field of study that requires the entire expertise of the entire globe really to bring to bear on this. It's a bold question that we ask, and it requires everybody.
I'll give you just a very specific example. We try to collaborate where we can. within ITAR for international space technology. But we have a special example coming up, and that is the starshade technology. We may see a scenario in a very budget-constrained environment where here in the United States, we build the starshade. We're leading that technology right now, but we get the telescope and launch from international partners. So that's a way that we could actually accomplish this in the near term. So in general, it's often challenging to work with other countries for a variety of reasons. But in this case, we may want to figure out how to do that.
Yes, the NASA History Office has just come out with a new book on international cooperation with NASA over the last 50 years. And it's really an important book, I think, because it shows what can be done if we do cooperate. I would have to agree with Sarah that it's become more and more difficult to cooperate, especially because of ITAR, the ITAR regulations. And I've been told that by people involved that the Cassini program, for example, today probably could not be done because of the ITAR regulations, which were not in effect during the time that Cassini was built.
Thank you very much. I yield back.
Thank you, Ms. Johnson. The Chairman Emeritus of the committee, the gentleman from Texas, Mr. Hall, is recommended.
Mr. Chairman, thank you. And I'll tell you, as I look at this aggregation of witnesses, you've really done a good job. I don't believe I've ever seen so much intelligence at one table and so much interest that we have, but I would warn you that when I was at SMU, you were the very type people that I didn't like. You ruined the curve for us ordinary people, but I always respected you. And Chairman, thank you. This is really interesting, and it takes me back about 15 years ago when we had a hearing on asteroids and found out during the hearing that an asteroid had come in 15 minutes of us sometime during the 80s, and we didn't know how many jillion miles that was, but it sounded kind of threatening to me. But you have such an interesting study, and you seem to be so interested in it, and I appreciate that. I guess my first question is, how would you characterize the importance of astrology in the general area of STEM education that we've gone through and created and worked on and nurtured here? And how would you motivate students? How are you going to get them as close to what the other witness had asked? It really should be easy, I guess, to answer to us, but how do you motivate students to pursue a career in astrobiology research? I guess, Dr. Voytek, you might give me a quick answer to that.
I think that the topic of astrobiology is so exciting and encompasses so many different aspects of science, technology, and inquiry that we almost have to do nothing but present the topic for people to be engaged and excited and kids to I believe it's one of the most exciting areas of research for children, and my own experience has been it requires almost no encouragement. It's an inspiration.
Well, I think you have the same problem that we've had, this Congress has had of the last probably 3 or 4 presidents, asking them for more money for the thrust in space, you know, and if we'd had just X number of millions or billions, well, we might not be begging Russia for a ride there and back up to the space station. But you must wake up every morning wanting to go to your work. It is as exciting as it is and as exciting as you feel. Professor Seager, let me ask you this. You stated in your testimony that, quote, as a nation we must continue to be bold in our space endeavors so as not to only inspire the next generation but also to keep a skilled workforce at the forefront of technology. Do you feel that we're being bold enough or too bold in meeting those goals, or can we be too old in meeting such an important goal?
Well, since you said it first, I'll say we can never be too bold. As we all know, China's headed to the moon right now as we speak. And we see China as, you know, in the academic world, they're great at copying everything, but we haven't seen them really innovate. But you never know what the future holds. I will say that most of my students now, and I do work with a lot of engineering students, they do not go on in astrobiology or exoplanets, nor do we want everyone to do that. Many of them go out to work in civilian space science or civilian industry or even for defense. So recruiting all these people through their interests, they want to work on really hard problems that have some impact. And you wouldn't know how many of these people they come to work on these problems because they loved Mars as a child, or, you know, they like the idea of searching for for life beyond Earth. So I don't think we can be too bold. And it's not only inspiring for the public, but it draws in the people, those very people that, make the curve higher. You want them to come and to work on our hardest problems for either science or for defense-related technology.
I just don't know how I'm going to tell my barber or folks in my hometown about your testimony here, but you must really enjoy getting up every morning and going to work. And I thank you for what I call a revolutionary study and presentation here. Mr. Chairman, I yield back.
Thank you, Mr. Hall. The gentlewoman from Oregon, Ms. Bonamici, is recognized.
Thank you very much, Mr. Chairman, and thank you to the witnesses. I concur with the comments about how inspirational this testimony has been. One of the issues that I've discussed since I joined this committee early last year was how we can do a better job educating the public about the benefits of space exploration and research. And I know you've touched on this somewhat, but I have to say that particularly now in a challenging budget time, when all of these things we're talking about have a price tag, how do we do a better job? How do all of us do a better job with that education? And Dr. Voytek, I was pleased to read in your testimony about how astrobiology research has benefited everyday lives, and you talked about the technology used in the Deepwater Horizon accident. Also, there was a mention in the testimony about the Mars Curiosity rover and instrument analyzing art that can help with causes of deterioration of artwork. What are some of the ways that we can go out and convince a skeptical public that we should continue these investments? Please, go ahead. And I'd like to hear from all of you briefly and allow time for one more question. Thank you.
Just very briefly, I often discuss our advances and our approach to astrobiology and our big questions as the search for a cure for cancer. It's a big, extremely important question. It's research that has to be done. And even though we've made tremendous progress, we haven't yet cured cancer, and we haven't yet found the origin for life on this planet or life elsewhere. But I think in the process, we have learned even more about ourselves that have led to other improvements in biotechnology and biomedicine. And the same is true for astrobiology because of the types of questions that we ask. And so in addition to the examples that you gave, we also have people working in synthetic biology that have come up with new rapid technology for rapid detection of HIV and hepatitis viruses. So there's a lot of advances in biotechnology. Our discoveries have revolutionized and made it possible for people to sequence the human genome. So there have been a lot of big payoffs as we move towards answering these very big questions.
Thank you so much. Dr. Seager and Dr. Dick, briefly.
I'll be brief. I think we need to keep hitting home the message that pure science leads to so many things, like the laser, like the human genome, and we need to make that as clear as possible to as many people as possible.
Thank you. Dr. Dick?
Yes, I've actually edited a volume called Societal Impact of Spaceflight, which I recommend to you, and another one will be coming out soon. There's a lot of talk often about spin-offs, but it's not just the spin-offs that you've heard here and other places. It's also the satellite, the navigational satellites, reconnaissance satellites, weather satellites, communication satellites. All of those, of course, would not have happened without the ability to go into space. And then finally, I would say also I find that going around the country, people are very interested in how we fit in what our place is in the universe, and that space exploration helps to solve that.
Terrific. And I want to follow up on some of the comments that have been made about inspiring and educating the next generation. And I know we've heard inspiration used a lot here today and being bold. And I know Mr. Hall mentioned Dr. Seager, your comment about the skilled workforce on the forefront of technology. How do we continue to engage young people, especially at a young age? And I think if you looked at the panel today, most people would think that two-thirds of scientists are women, which is, of course, not the case. Yeah. So how do we continue to get young people involved? Can you recommend any changes to? I'm also on the education committee. Any changes to STEM education? Efforts to maximize students' interest? We're talking about things like incorporating arts and design, more hands-on learning. Do you have suggestions about how we can engage more students in STEM education? Dr. Seager, I'd like to start with you.
This is such a huge topic, it would be impossible for me to articulate all my thoughts, in the time that we have. So I may just say I'd be happy to talk to you about it at another point. It's a big, big, big thing, and we really need to do something new and different.
Thank you.
I'll just say that all children are born curious about the world, and somehow that ends up getting squashed out of them. And so we really have a problem.
Thank you. I will definitely follow up. Dr. Voytek.
I just want to say one thing, and I think Sarah would agree with me, is that it's extremely important to start as young as possible. If you wait to bring science and technology to students that are in high school or college or even junior high, you've already missed incredible opportunities to develop their interest or curiosity and set them on the path in those sorts of careers.
Yeah, I will just add one more thing. Children, we all know we're all one at some point. They love dinosaurs. Often children love space and planets, and we just need to keep that alive and do a better job at it.
Thank you. Dr. Dick.
A very specific recommendation would be more curriculum development. There are a few curricula on life in the universe which, it pulls in everything. One of the great things about astrobiology, astronomy, biology, chemistry, you can talk about almost anything, and the development of specific curriculum that could be used in the schools, I think, would be a very good way to start.
Thank you so much. I see my time has expired. I yield back. Thank you, Mr. Chairman.
Thank you, Ms. Bonamici. The gentleman from Mississippi, the chairman of the Space Subcommittee, Mr. Palazzo, is recognized.
Thank you, Mr. Chairman. I appreciate our witnesses and their testimony today. This is a very exciting subject, and I agree with everything that y'all presented to this panel so far. Dr. Seager, I love your comments about we cannot be bold enough, and you're talking about investment. And we need to do a better job of investing in astrobiology. So could you expand on those two? Where would you invest? And if you had a limited amount of resources and you had to take from one area to put into another area, feel free to comment on that. But also, and I may open this up to everybody, is that when you have an agency that is so risk adverse and you throw the words bold out there and being different, how do you reconcile those two?
Well, that is such a great question. I would like to have an opportunity to later on perhaps provide a written response, but I can try to answer it briefly right now. Okay, so in terms of being bold in space, there's a new huge thing happening, and that is, we call it CubeSats. They're tiny spacecraft that now people all around the world are building and launching. Students can do this. So, risk can change now because we can launch small things cheaply, be very risky with something that's not that costly. And in that way, you can kind of educate the university level people, even down to some special high schools, in a very colloquial way. So, that's when we have other ways we can do high risk and generate that. The other question, I think, was about moving money around. That one I can't answer. I think
can or don't want to.
Like I said, I'd have to give it some more thought. But one thing I do want to say is what makes our nation unique is, just our ability to innovate. And that innovation is something that it's very hard to do because you can't always put your finger on what actually it is. You can't articulate it in a way that can actually be supported. But that's why we ended up, being able to get to the moon. That's why we end up being a leader in so many things. And so that's the thing I would try to, however possible, keep that alive, keep that really, really, really moving forward here in America.
And if Dr. Voytek, Dr. Dick would like that.
Let me just bring up human space flight. When I was a kid, I was told that we would be on Mars with humans by 1984. Obviously, we didn't make it, but I do believe that we should have as a long-term goal to go to Mars, or at least as an initial step, the moons of Mars. The moons of Mars were discovered just a few blocks from the White House at the Naval Observatory, so there's a sort of a peculiar American interest in the moons of Mars, which are just a few thousand miles above the surface of Mars, and would be a great reconnaissance, sort of a natural satellite space station for looking at Mars. So I believe we should push towards Mars, maybe the moon first again, and then Mars.
I'd actually like to take an opportunity. We focus mostly on missions and exploration. I think that the important thing of our research program, the Science Mission Directorate, is that we actually are able to take risks because the investments aren't on the order of millions and hundreds of millions and billions of dollars to do exploration. We can explore lots of these questions on Earth for, a tenth of that cost, and we are bold and we do take risks, and sometimes it pays off tremendously and sometimes we make mistakes, but we try because, again, this is a bold question. We are bold with our scientific portfolio and the research programs.
I did think of one thing to add, and that is a sort of rise of we call it just the private commercial spaceflight world, like SpaceX. I think the risk now can be transferred to them in a way, still with some level of NASA support, when you're supporting them going to the space station and things like that.
Real briefly, I'll try to get one more question out. And, we talk about, budgets up here on Capitol Hill. Our nation is definitely in a financial crisis, and we continue to fight amongst each other over shrinking discretionary budgets when the largest driver of our deficit and our debt is mandatory spending. So we have to come to terms with that. But when you got such great programs like this, and competition and national security doesn't actually seem to propel Congress or this administration to act in the best interest of the nation anymore, what would you think would trigger us to focus more on exploring Earth-like planets and getting more engaged in astrobiology?
Well, one thing that would help is, making that very strong message that it's a legitimate science now. We're not like searching for aliens or looking for UFOs. We're using standard astronomy. We're using models that have been used for Earth's atmosphere and planetary atmospheres. I think making that message that it's really a legitimate field of research is one of the critical aspects.
And just the very idea of exploration. I think astrobiology embodies the American ideal of exploration, and I think that really is a goal enough to inspire the young people and the citizens.
The one thing that's sometimes very hard to see and communicate is it is really a long-term investment in our national security. And, we see it even in industry that civilian space science is like a way you can do stuff openly. And so that is, it's very hard to communicate very, very long-term investment, but that's essentially what you're doing here.
I see my time's expired. Yield back. Thank you for your...
Thank you, Mr. Palazzo. The gentleman from California, Dr. Bear, is recognized.
Thank you, Chairman Smith. And I'll reiterate what everyone on the committee has already said. Fascinating subject. As someone who trained in biology and then went to medical school, I think, Dr. Seager, you touched on, we're all born with this natural curiosity, from the youngest of ages, where did we come from, where are we going, the origins of life, whether it's on the scientific realm, whether it's on, in our faith-based traditions and so forth. It's naturally innate to who we are as human beings. So we don't have to rediscover this. We don't, our children have this naturally. What we have to do is grow that curiosity. And in order for that to grow, we have to dream big, right? I mean, for those of us who grew up in the 60s and 70s with the space race, there was a dream. We didn't know how we were going to get to the moon. We didn't know what technologies it would take us, yet we dreamed about going there. And we've got to recapture that American spirit of dreaming big, of not knowing how we're going to make these discoveries, but truly committing ourselves to making these discoveries so that our children, so those next generations of scientists have this natural curiosity. And we can't be limited by saying, oh, we don't have the money here. Or, yes, we've got financial limitations, but we've still got to learn how to dream first. And then we can work within those limitations to say, what's the best way to use those resources? So that wasn't a question. That was more of a comment. The question is, when we're looking at the origins of life, when we're looking at the future of worlds and how that affects our own planet, these are beyond country borders. These are beyond nationalities. These are beyond faith traditions. What can we do within the context, if another country happens to discover evidence of life on another planet? We're all going to benefit from that discovery, and it is going to propel us forward. What are the contexts where we could work together? Because we're talking about big data sets. We're talking about analyzing major data sets. What context at the international level would you like to see in terms of collaboration in the search for life? I'd ask any of Dr. Voytek.
I would say that we attempt with all missions that are being planned by spacefaring nations that we can to collaborate with them, either contributing personnel or instruments. So we have a very good relationship with ESA, and they have flown instruments on our vehicles and spacecraft, and the counters we have flown as well. So their ExoMars mission that's planned to launch in 2018, we have an instrument on board. Our plans for 2020 to bring back samples. We've been working with the international community to figure out how to share the results and participate together in the analysis of those samples. I think that we have ITAR restrictions, but science is an area that crosses boundaries pretty easily. There's the natural curiosity, and our scientists are doing a lot of the work for us.
Well, Dr. Seager, let's say we do build this next generation of telescope. Again, we're going to we will be bringing in massive amounts of data, and it'll take a lot of eyes and a lot of analysis. I know in other aspects, we've allowed those amateur astronomers and the public to go out there and look at this data. Again, that's a way of even getting high school students, elementary school students looking at this, imagining things. What are some contexts that we can do to, again, bring in the entire planet?
Well, I'd like to address it from a slightly different view, and I think it's great for scientists to interact internationally because we don't have a political agenda as scientists. But I think when it does come to space technology, it's just, this is my personal opinion, it is so much more efficient because we don't have this extra layer of bureaucracy and inefficiently to do it all ourselves here in America. However, if the budget realities and practicalities don't allow it, then I support the international cooperation in space technology. In terms of the big data that is public, like the Kepler data, for example, any one of us here, we can download the data, we can look at it all around the world. I think that is really great, and that does make the world come together in a unique way.
Great. Dr. Dick, would you want to add anything?
Well, I would just say that it very much depends on the scenario when you're talking about international cooperation, whether it's microbial life or intelligent life, and the implications of finding that. There are various international organizations that can be worked through, like the International Academy of Astronautics, and there's work being done on what we should do if and what the impact would be if either microbial or intelligent life would be found.
Great.
I just want to say one more thing. I want to reiterate the point that you brought up, which citizen science is incredible. I think it's a way to engage the public. I think that we have shown in astronomy in particular how, it's a tapped workforce that has done tremendous scientific work for us. And I think particularly with telescopic data that we will continue to use it in the future and maximize it. It has been awe-inspiring and neat to see how people have just gotten involved and are planet hunters themselves. I think the public is dying to get involved even more.
Great. Thank you. I yield back.
Thank you, Dr. Barra. The gentleman from Florida, Mr. Posey's, recognized for his questions.
Thank you very much, Mr. Chairman, and thank you, witnesses. It's a fascinating testimony, fascinating written testimony. I hated for it to end, actually. Wish you could have added some more pages to your testimony. It was fun to read, very enjoyable. I think, you've pretty much indicated that life on other planets is inevitable. It's just a matter of time and funding, and clearly that's it. If our species survives long enough, and I wonder, a question to the three of you, what you see as the greatest dangers to life on Earth?
Well, we've had the recent experience of the fireball over Russia. I would have to say that the asteroid impacts are a danger. We have, there's a range of material coming in. We are like a pinball machine, and we're in outer space. The Earth is in outer space. And you have all this material coming in, and occasionally a larger one comes in, as over Russia. But it's entirely possible, as evidenced by some of the craters on the Earth, the ones that wiped out the dinosaurs, they happen over much longer periods. But I believe that's one of the motivations for human space flight, is to get at least some of us off the Earth in case there's a catastrophic event such as that.
Well, we do like to believe with, sort of we do like to think with our current resources of monitoring asteroids that we will find something big before it finds us. But that's certainly an important area to keep up. If I can give my personal opinion, I think overpopulation of our planet is going to be our biggest problem.
And I would say with all systems that resources, particularly essential resources, can be limiting. And so I think as we look other places for alternative energy or other means to support a large population, that's a threat to our planet.
Okay. Conditions on other planets are going to seem harsh at first, and we know in history conditions on planet Earth have been harsh. If we came here or explored Earth 64 million years ago, we'd say, wow, it's too cold. And if we were 65 million years ago, we might say, wow, it's too hot. So I guess there's going to be windows of opportunity on the other planets too. Any comment on that?
Well, It's one of the great things about this research being done just in the last 2 decades on life in extreme environments, just how tenacious life is, in extreme temperatures and under the oceans in these hydrothermal vents at extreme temperatures and pressures. You find not only microbial life, but these long tube worms. I mean, it's just amazing where it seems wherever conditions are possible, and by conditions I mean a much broader range than we used to have, that life does arise, and arise fairly quickly.
Okay.
I would say that we talk about life in extreme environments, and I'll note that it's mostly microbial, and it's mostly extreme by our own reference. So it's an anthropocentric definition of what is extreme, because in fact we have had the capability to inhabit warm places, cold places, because of our technology. We basically bring everything back to conditions that support a comfortable life for humans. And so exploration, colonization on other planets in harsh environments will require that we do the same. We're not going to suddenly develop the capability to live at, over the temperature of boiling water. We'll have to make our local environment hospitable to ourselves, and we have that technology now.
Dr. Seager?
I'm going to defer on that question.
Okay. What do you believe was the highest historical temperature on the surface of Earth prior to the extinction of the dinosaurs, Dr. Dick?
It's hard to say. That's not my area of expertise, but I can say that on Venus, for example, the temperature is now 900 degrees Fahrenheit, with a sulfuric acid rain and very harsh conditions. And Mars, of course, is much colder now than the Earth. So one of the goals of astrobiology is to try and figure out how planets that seem to be so similar in the past have diverged.
Dr. Seager?
No, one thing I always tell my students is that every day is like a PhD defense. So I actually don't remember that number off the top of my head.
Okay. And Dr. Voytek?
Ditto. Except that, as you mentioned yourself, Earth has experienced extremes in environmental conditions from the early formation. And so certainly environmental conditions well beyond the limits of human life.
But these changes do happen very slowly, and we believe that life will adapt.
Well, thank you all very much for your testimony. Mr. Chairman, I yield back.
Thank you, Mr. Posey. The gentleman from Kentucky, Mr. Massey, is recognized.
Thank you, Mr. Chairman. I find this topic fascinating. I have a question that may ask all of you, but I want to ask Dr. Seager first. If you were king for a day and could offer an X Prize for something in your field, what would it be?
It would be for finding the nearest Earth-like planet, around the star that is closest to our own planet. So I'll try to answer that one more time in a more clear way.
Yeah.
We'd like to know, just sort of as a legacy for the future, which of the very, very, very nearest sun-like stars have a planet that is like Earth with habitable conditions and surface liquid water required for all life as we know it. So I would offer that prize for being able to find that. That would have to be a prize that was sort of on the order of billions, not just millions.
Okay. And Dr. Dick, what would you...
I'm going to stick with Europa. I think it's less than 1 billion miles away, and if we could offer a prize for somebody to get there and find a way to drill down below the ice. We don't know exactly how thick it is, but that would be a feat in itself. They could drill down through that ice and see what's below the ice.
And Dr. Voytek?
I'm going to pick Enceladus. I'd like to offer a prize for someone to go sample the plumes.
Okay. Thank you. And so, Dr. Seager, you mentioned a star shade, and this captured my attention and imagination. So, is this something that would be deployed in space? Could you describe that?
Yes, I didn't mention that. Pretty much, we do need to go to space to get above the blurring effects of Earth's atmosphere. Now, the star shade is something that's been developed for a number of years, supported by NASA. The concept actually was first written down in the 1980s by a French physical optics researcher. So do you want me to just elaborate on the star shade?
Yeah, maybe 30 seconds.
Okay, sure. So first of all, the star shade does have heritage from large radio deployables in space, okay? Those are like 20-meter structures that unfold into a parabolic shape. The star shade is a flat shape, It's not a circle or a square because that has light will go around the edges and just cause problems. It has to be very specially shaped. It ends up looking like a flower. Okay, now demonstrations have been made in the lab of how you would fold up the petals, how they would unfurl, and the petals have to be made very, very precisely, because remember, we have to block out the starlight to basically better than a part in 10 billion. Now, the star shade, it would essentially just be like, looking at a single light and blocking it with your hand. And the star shade would have to fly far away from a telescope. You could actually use any type of telescope. Now, this just can't go in any orbit because formation flying is tricky. And so you really want to get away from Earth, either in an Earth trailing or Earth leading orbit or at what we call L2. So the star shade is, it's been under development and it's still going.
And so you have to pick a light to block, right? So you would
Correct.
have to place some bets on a star.
Well, so we're now in this committee that I'm chairing, that's Science and Technology Definition Team. We're spending a lot of time on that exact question. And so the question really is, which stars are you going to go to? Because you move the star shade around the sky or around in space, or the telescope can be moving around. There's sort of a scenario where you send up 2 or 3 star shades, so you always have something going on. There's a scenario where as the star shade is making its way to another, to line up with another star, your telescope is going to be like a very new version of Hubble and doing general astrophysics. So yes, that's a problem, but it's not a limiting problem.
And you would be leveraging the Hubble that exists.
Well, we wouldn't use the Hubble in this case only because Hubble is in low Earth orbit, and Earth's reflected light is a problem, as is Earth's gravity for formation flying. But we could essentially use even, I don't want to use the word, any old space telescope because it's still a problem, but the telescope doesn't have to really be special in any way. It just has to be in the right orbit.
And is there some sort of, I know it's in itself, the concept is bang for the buck, but is there within that a bang for the buck version of it that you could do that would prove its concept or give some quick results for?
I mean, this is something we've definitely thought a lot about, and because of the scaling issues, like showing it. It's difficult to do anything in space except the real thing, because to demonstrate on the scales required and to get that 1 in 10 billion, really the real thing. However, there are many things that we can do just on the ground and that are ongoing and need to continue. Like, we call it subscale, smaller versions demonstrations in the lab. There's, testing in the outdoors. You have to go many kilometers separated. So there's things we can do. But the problem of finding Earth is so hard, there is really no easy or cheap way to actually do it.
Thank you. And Dr. Dick, in my last few seconds, I'd like to touch something that you mentioned in your opening testimony is reconnecting that gap between SETI and astrobiology, or it looks like astrobiology has kind of subsumed that space. What is the state of SETI right now?
Well, Objective 7.2 of the Astrobiology Roadmap does mention biosignatures of technology, which technically is SETI, but I think the problem is that NASA does not really support that with funding based on the termination of the SETI program by Congress 20 years ago. So if Congress would wish to get SETI going again with even a little bit of funding, that would be an important addition, I think, to astrobiology, because right now it's really an artificial separation. We're looking for microbes, but after that, we're not looking for the intelligence with the NASA program.
Great. Thank you very much. Yield back. Okay.
Thank you, Mr. Massey. The gentleman from Texas, Mr. Vesey, is recognized for his question.
Thank you, Mr. Chairman. I had a question for Dr. Voytek, specifically about oil and gas exploration, and your thoughts on if you think that it's practical that some of the technology that's being adapted can be specifically used to detect leaks at great depths as it pertains to oil and gas exploration, particularly offshore.
So one of the examples I gave in my testimony was a technology that was developed at Woods Hole Oceanographic, and it was a combination of an autonomous vehicle and a mass spectrometer that could detect hydrocarbons, and it was used to identify and map the leak from the Deep Horizon spill. And I think that was its original design for the astrobiology program was to try to search for the source of biogenic gases and chemicals. So to identify the sources in the deep sea from hydrothermal vents of, say, the production of methane or hydrocarbons that were produced by microbes. And so I think that was a great example of that technology being adapted to a very important environmental problem.
Thank you. Did you want to add something? It looked like you wanted to add something, Dr. Dick. Okay. I did have a question for you, Dr. Dick, specifically about the emergence of astrobiology and how you thought that NASA's early initiatives, such as the Viking landers on Mars, affect the evolution of research at NASA related to the search for life in the universe.
Well, the Viking experiments had a great impact, I think. The biology experiments were 3 biology experiments. One of them, one of the principal investigators to this day believes he found biology on Mars, but the gas chromatograph mass spectrometer found no organic molecules on Mars, which means if you don't have organic molecules, you can't have life. So that sort of put a damper on the Mars program for a while. I think it was something like 15 years at least before we went back to Mars with another spacecraft. So those kinds of things really can have an impact. But now, with the rovers that we have there now, including Curiosity, they're looking for those organic molecules. They haven't found any complex organic molecules, maybe some very simple ones. But of course, we've only looked in very specific places. So in those specific kinds of events in the development of astrobiology can have a great effect, as in the case of the Mars rocket ALH-84001 in 1996. I think that gave a great spur to astrobiology, the development of astrobiology over a much broader program than the old NASA exobiology program, which was pretty much limited to origins of life, and that's the astrobiology program that we have today.
Well, and speaking of that, like, how does that history sort of inform planning for the next decade of astrobiology research?
Well, I think if we find anything on Mars in the nature of organic molecules or other things like that, history tells us that would have a great impact on funding for the future. So we're all hopeful that such things will be found, aside from all the other interesting things that those rovers are finding.
Thank you. Thank you, Mr. Chairman.
Thank you, Mr. Veazey. The gentleman from Illinois, Mr. Holgren, is recognized.
Thank you, Mr. Chairman. Thank you all for being here. This has been very helpful and very interesting. I also have the privilege of serving as one of the co-chairmen along with my colleague, Mr. Lipinski, who is unable to be here today, but of the STEM caucus. And all of us, every member of Congress that I speak with, is passionate about how do we get young people interested in science and technology and space and engineering and mathematics. And clearly this field is that you all are talking about is, I think, a great avenue to get young people interested. One question I'd have for you of getting into that is when, looking back in your own history, when was the first time you really were interested in this and kind of made the decision, this is what I want to do personally?
You know, my first memories are about the moon and stars. But it wasn't until so the seed gets planted early, but it wasn't until much later, maybe in my late teens, that I realized it was a career choice.
I grew up in rural southern Indiana where it was very dark, so the night sky is what inspired me to start with from a very young age, and it just grew from there. And I'd have to say also I was very much influenced by science fiction. One of the things I found when I worked at NASA is a lot of people at NASA were inspired by science fiction. And those novels about, life on other planets and that sort of thing. So for me, it was from a very early age.
And for me, my father was a physician, and he gave me his medical school microscope when I was about 7. And I started exploring my backyard and the streams and the refrigerator and the food and saw that life was everywhere. Everything was moving. It was kind of scary for my diet, but it set me off from my natural interest in how life persists on our planet.
One thing you'll find from most scientists is there is one special individual who helped them along. In some of our cases, it was a parent. But let's face it, most kids in America, your parent's not a scientist or a doctor. And in that case, it's a teacher. So we need to have a better way to, we'd all like to see teachers be like the best paid people in the country to recruit the people who are really the very best. But we really need to find a way to reach the teachers. Our children are just spending, so much of their waking hours in school. Everyone needs to encounter that one special person to enable them.
I absolutely agree, and that was really where I wanted to go next. Is the idea is much of this is sparked grammar school age, so maybe up to 6th grade, 7th grade, 8th grade, maybe a little bit later in high school when you really see, hey, this is something I could pursue. Part of the challenge is, I think a lot of teachers are intimidated, certainly when you start talking about astrobiology. That would be something for a fourth grade teacher to have to inspire kids. That would be intimidating. And so any ways that we can be providing resources to teachers, I think, is so important, or even bringing in people like yourselves to be talking to young people to let them know how exciting this is and how their generation could be the generation that makes this great discovery. It could be one of them, and how exciting that would be to do that. So any way that suggestions you have, and really did want to, Dr. Seager, take you up on your offer of a follow-up of talking about education.
Yes, well, I just want to offer three comments. The first comment is that, unfortunately, our education system here in America, including the universities, is the same as it's been for hundreds of years.
Yes.
Number two, children, as you know, they love the ones who have iPad or the internet. The whole big data social media thing is something that could actually be big in schools where the teachers are not up on things. The third thing I keep repeating is it's very hard for us here to have the long-term investment. But the long-term investment is to change the culture for our university undergraduate educated people that they can and should be teachers at the elementary level.
Yeah. Well, and I do think this is the type of thing, again, there's a disconnect with, we want to have, great education for our kids. We also struggle with limited resources that we've got. How do we figure out compensating teachers, getting the right people there, bringing people from the outside who aren't necessarily certified but can inspire to be engaged in the classroom as well, bringing business, bringing our laboratories, bringing NASA, every possible way, whether it's through technology or other ways. You're right. I mean, the door is open like it's never been before to get that into the classroom, but we've just got to do it. Let me switch gears real quickly because, Dr. Seager, I want to ask you a little bit more about the, you mentioned the coronagraph, is that right? And then also the star shade. And you also mentioned collaborating with the international community as a cost savings measure on that. I wonder if there's any other countries that are doing work in those specific areas that we should be aware of, and has collaboration on such projects already been discussed in the scientific community, and how can we encourage that or push it forward?
I would say that it's ESA, Europe. In the past, when we were supporting a so-called terrestrial planet finder mission, we did have an agreement with the Europeans. I forget the other part of your question.
Well, it was just if there, so it sounds like Europe is open. Has that already started? Is there investment there?
So Europe has recently made their choice for their next big missions in the coming decades, and they did not choose anything in exoplanets.
Okay.
I think that really just means the door may be open for an international collaboration.
Okay. Part of our challenge, I'm way over, but I think it is frustrating when we try and have these international collaborations when we're running on CRs where we literally don't know month to month if we're going to fund programs. Somehow we've got to get back to regular order. We've got to get back to, I think, specifically with sciences, pull it out of this year-to-year funding, worse month-to-month funding. What I hear is every other nation has 5-year, 10-year, 20-year fully funded science budgets. When we come and talk to them about collaboration, oftentimes they'll laugh back at us because they know we don't even know what's going to happen after January 15th because that's when the CR expires. So we've got some big struggles. Would love to have your help on all of these suggestions you would have for us to move forward. My hope is that you get a sense that there is a desire, that we are excited about this, and we want to work with you and want your help to do this well. So with that, thanks, Chairman, for your graciousness, and I yield back.
Thank you, Mr. Holmgren. The gentlewoman from Illinois, Ms. Kelly, is recognized for her questions.
Thank you, Mr. Chair. And going along with my colleague from Illinois, my question is, I started a STEM academy in my district, but my question, all due respect, Dr. Dick, but how do we get more women and minorities involved? Because it seems like there's, we need so many more women represented and minorities in the field, particularly African Americans. Are there any best practices anywhere?
Well, I know the NASA Astrobiology Institute does have summer workshops both for students and for the teachers. I'm not sure exactly how you encourage the women and the minorities to get involved in that, but I'm sure the program could be expanded, and in that way you might get more. But I'd have to think about it more.
Maybe I can speak to our programs. The astrobiology program actually has a minorities program, and we are working with the United Negro College Fund to actually, it's at the level of, so we believe in teach the teachers and a cascade effect of training and providing role models. for students so that they can see that this is something that I can do. So one of the things that we do is this Minority Institute program, which brings in scientists to work side by side with other astrobiologists, and they are encouraged to develop curricula to take back to their universities. And we work very closely with historical black universities and other minority serving institutions. We also have internships that are focus on underrepresented groups. And I would be happy to share with the committee all the work that we have done up until this point in astrobiology, both with missions and just within our own program, that target curricula development, workshops for teachers, and how the efforts that we have made to make astrobiology part of a STEM approach.
I'll just be brief and say we just need role models. You need children to be able to see people in their own community and schools that plants deeply in their mind, oh, I could be like that. I think that's a big thing. And then we need to change the culture at the higher institutions so that it's okay to be different initially. And then we need critical mass so there is no difference.
I definitely agree with that. We work with 5th, 6th, 7th, 8th graders, and they don't even realize what the possibilities are until we expose them to the possibilities. And they're so thrilled with what we're doing. But it's just that we have to move it from school to school. We can't just keep coming back to the same students, but thank you so much.
And thank you,
Ms.
Kelly. Thank you, Ms. Kelly. The gentleman from Texas, Mr. Weber. Well, all right.
Mr. Chairman, I'd like to ask one question on behalf of the whole Republicans and Democrats.
Of course.
Do you think there's life out there? And are they studying us, and what do they think about New York City?
Wow.
Well, let me just say that in our own Milky Way galaxy, there are 100 billion stars. And we now believe in our universe we have more than 100 billion galaxies. So if you just do the math, the chance that there's a planet like Earth out there with life on that is very high.
I didn't do the math. There's just three things about math I couldn't do, and that's add and subtract.
Well, if we had more time, we could work it out. But let's just say that the chance for life is very high. The biologists never like us to speculate in that way. But the real question really is, is there life very near here in our neighborhood of stars? And that's the question that we are really addressing for real for the first time.
On behalf of the biologists, I think it's fine to speculate. We think that life takes over any chance it gets, and so I think we believe there's a high probability. And I think that one of the amazing things about our own planet is whether they're looking at New York or some small town in Indiana, the diversity of life here and the way that we have chosen to live our lives is just phenomenal. And I think it goes all the way down from humans to microbes.
One of the great things about finding the other planets is that it corroborates what many of us have used as a guiding principle, that what has happened here in our own solar system has happened elsewhere. A lot of people didn't believe that for a long time, until 20 years ago when we started to find the planets, and now we find that they're everywhere. So it's another step, of course, to life, and an even bigger step to intelligence, but I think the guiding principle holds that what has happened here will happen elsewhere in this huge universe.
I yield back.
Thank you, Mr. Hall. Good question to end with. And let me thank you all for being here today. This has been I'm sorry, the gentleman from Utah, Mr. Stewart.
I've been patiently waiting. Mr. Chairman, I assuming you're yielding?
I recognize you, I thought.
Thank you, sir.
We'll even give you an extra minute for the oversight.
Well, thank you, and it's been interesting, and Mr. Hall actually jumped on something that I wanted to maybe conclude with, and before I do, thank the witnesses once again, the panelists. It's fun to hear something and not to leave a hearing frustrated or like you want to throttle the other side like we do in some of our hearings. Of course, it's overly politicized, and I appreciate the recognition that it's in our human nature to explore and to discover. I want to come back and just be more specific if I could, just very quickly. Based on your experience, based on your training and kind of your gut, do you think it's even conceivable that there is not other life somewhere in the universe? Is it even possible?
It is conceivable. Since
okay.
We've just conceived
we can conceive it, yes.
I mean, we really don't know. This is why it would be such a great thing to find life on Mars, because if you find even microbial life on Mars or that sort of thing at a low level, which is an independent beginning of life, an independent genesis. That means that life began on two planets very close together where conditions were possible, and that you can, from that, extrapolate out to the rest of the universe. But it is possible, if we don't find life on Mars and eventually over the years don't find life anywhere else, that it either doesn't exist or it's very rare. Now you can define rare yourself. If you only 1 out of a billion stars in our solar system has in our galaxy has life, then you still have 400 planets with life on. So.
Well, and I want to go kind of quickly on this because I'm actually trying to get to another point. Do you believe that there's life out there, Dr. Dick?
Yes, I do.
Okay. Dr. Seager?
Yes.
Okay.
Yes.
Okay. I think most of us do. I mean, and you look, as you've indicated here, you look at the numbers, it's impossible almost. Forgive me for using inconceivable. But it just seems essentially that there would have to be somewhere. And then the presumption here of this hearing is that eventually we're going to discover each other, whether we discover them or they discover us, or however that process might be. And I think in a lot of these conversations, we assume that the discovery might be that we find some basic form of life, something, not at all like us, I mean, bacteria or microbes or whatever that might be. But it's possible as well, isn't it, that we find a more sophisticated form of life. Is that true?
Yes.
Yes. Okay. Yeah. Again, it would have to be at least possible.
Sorry.
Go ahead.
I'll just say that my view is that microbial life would be more abundant than intelligent life because it's harder to get to intelligence. Sure. But on the other hand, you have these vast scales of time that are involved also.
Yeah. Exactly.
There's a chance that intelligent life is very rare and not within our sphere to communicate with.
Oh, and that's actually my next question, and that is let's assume that we find life. What do we do then? I mean, do you have conversations about what the next step is? Are there any conversations about how we would attempt to communicate with life, or how does that change things for us and the way we view ourselves?
I know that
we do that with Twitter.
Yeah. No, this is intelligent life.
That's great. We certainly discuss what would be the implications for society, what are the philosophical ramifications, the religious ramifications, and we have funded studies through the Dialogue in Science and Ethics and Religion through the AAAS. And so we think about those aspects. I think that, and I'll say that, and I don't know about if we've thought about how to communicate or invite them home for dinner or what, but
so that really isn't either of it's not within your realms of considering what we do after we discover. Is that true? Or do you consider that?
Well, I don't know if it's the best place for us to talk about it, because this is one of the things that is sort of in its infancy and maybe even a bit marginal, but people do talk about it. Maybe you send up even bigger space telescope, 50 1-meter telescopes in space to get pictures in detail of the planet. There are people here on our planet now, in our country, who want to be able to send a robotic probe to another star with a planet. It would take a very long time to figure out how to do that and to actually get there. But there are conversations going on. They're just not at a really formal or well-articulated level.
With the exception of the fact that, since probabilistically we believe it's more likely we'll find microbial life, people in my field are extremely interested in getting a sample of that and being able to immediately compare it to what life is like here and start abstracting more information about exactly what life is. How do we define it? How is it different? What have they learned on that planet that makes it survive there? What can we learn in our own system? And so I think that there is a plan as a comparative, finding a species or another example. And so
Yeah. And this is exactly what I'm working on at the Library of Congress for my year right now. And I would also say that there are in the past there are protocols, official protocols, which have actually been gone through the United Nations about what happens if you find extraterrestrial intelligence. Basically, the plan is to confirm it first and then tell everybody, not keep any secrets.
Yeah. Okay. Well, and that would be interesting, wouldn't it, if some people knew and others didn't?
Right.
Well, and it's as interesting as it is to talk about the discovery. I think the more fun conversation is what happens after that and what we do with that information. So, thank you, and Mr. Chairman, thank you for allowing me the opportunity.
Thank you, Mr. Stewart. Good questions. Thank you again to the witnesses for your attendance today and for speaking about such an interesting and fascinating subject. I think you have enlightened us all, and we look forward to staying in touch with you about the issues involved. So thank you again, and we stand adjourned.